Hi, this is Professor Atif Iqbal, and my paper ID is 0304. The paper title is a novel high gain boost converter with switched reactive network for electric vehicle applications, a new member of modified boost converter family. The paper is published with the help of the internal grant that's called Qatar University Collaborative Research Grant. The content of my presentation is introduction, proposed converter, working principle of the proposed converter, mathematical analysis of the converter, design aspect of the converter, followed by the simulation result and experimental results, and then finally the conclusion. So the high gain DC-DC converter is generally used in renewable energy sources and such as the solar photovoltaic system or fuel cell applications, and this can be used in electric vehicle applications and also for the grid connection to the renewable energy sources. So the DC-DC converter are generally classified into major classes, that is called isolated converter and non-isolated converter. In the isolated converter that have the isolation between the between the two sides, they provide high voltage gain, they provide the isolation. The DC is pure and this is for good for sensitive loads, but the problem is the bulky structure and lower efficiency. For the non-isolated converter, the conventional converters are the buck converter, boost converter, buck boost converter, Chuk converter, Sepik converter. They are non-isolated and they have moderate voltage gain. Then to enhance the boosting capability of the non-isolated converters, they are classified as the derived converters with cascading of the two or more converters to enhance the DC gain, and the with inverter stacks and with voltage multiplier. So in the cascaded structure, the boost converters are cascaded together. This is called modified converter family. They provide high voltage gain, but the efficiency is poor. Then with the inductor stacks and with voltage multiplier, the multi-level buck or boost converter, they are used with inductor stacks. They offer a high voltage gain. The proposed converter is actually the combination of these two with inductor stacks and with voltage multiplier. So the proposed converter is a combination of inductor stacks and voltage multiplier, which that will provide high boosting factor with reduced number of component count. This is the converter structure, and if we see that it contains a inductive network, two inductors with three diodes. So this is a switched inductive network. We call it switched reactive network, and these are the different diodes and capacitors. So the advantage of the proposed converter, which we call it modified boost converter with switched reactive network, is high voltage gain with few number of components, and it only utilizes a single switch. The switch is due to single switch, the control is simple, and it provides a continuous input current. So this is the modification of the same converter can be done by the help of the switched reactive network connected in cascade. This is one unit. This is the second unit, and this is the nth unit. So this is called like level 1, this is called level 2, this is called level n. And while increasing the number of levels, we need only one inductor and 3 diodes in each unit. So if the number of level is 0, that refers to conventional boost converter that uses only one inductor, 3 diodes, 3 capacitors, and the output gain is given as 2 by 1 minus D, where D is the duty ratio. Now, if we have like one number of level, which is our proposed modified boost converter. The number of inductors are 2, the number of diodes are 6, the number of capacitors are 3, and this is the expression for the voltage gain. If we have 2 units, then the number of inductors will be 3, and the number of diodes will be 9, the number of capacitors will be 3, and then the expression for the voltage gain. So we can generalize this with n number of levels, and n plus 1 inductors are used, 3 n plus 1 diodes are used, and 3 capacitors are used, and this is the voltage gain formula. So now here what you see is the charging of the inductors by the red dots, and the discharging of the capacitors by green. So what you see that in this mode we call mode 1, both these inductors, they are charged through the switch, and they charge in parallel. While this capacitor C1, it discharges to the capacitor C2 through the switch, and the load is being supplied by the capacitor. So this is called mode 1. And at the end of this mode, L1 and L2 are magnetized to their maximum level. C1 and C0 reach their minimum level because they were being discharged during this mode, and C2 charges to its maximum level because C2 is charged through capacitor C1. And this is the governing expression for this mode, and the voltage across the 2 inductors are same as the input voltage or the source voltage because they are connected in parallel. And capacitor voltages VC1 and VC2, they are same, they are also in parallel, and the output voltage is same as the voltage across the capacitor. Now this is mode 2. So we see that the inductors L1 and L2, they are in series, and they charge the capacitor C1. And moreover, these 2 inductors, they also supply to the this capacitor C0. So capacitor C0 and the load. So the 2 inductors, they discharges in series, and they are charging the capacitor C1, and simultaneously they are supplying power to the load, and while the C2 and C0, they are being discharged. So at the end of this mode, L1 and L2 are demagnetized to their minimum level because they are being discharged. C1 and C0 are charged, and so C1 and C0, they are reach their maximum level, while C2 is discharging this energy to the output, and so it discharges to its minimum level. And during this mode, the voltage across the inductor 1 and 2 is obtained like this, and for the n level topology, the voltage will be like this. So now by applying the inductor volt second balance principle, the inductor L1, the capacitor voltages VC1, VC2 is given like this, and so the voltage gain is obtained like this. So this is for n is equal to 1, and for n is equal, for n general formula for n number of levels, this is the voltage gain. So what we see that the voltage gain does not depend only upon D, but it also depends upon N. So certainly we keep on increasing N, we can get higher and higher output voltage. And this is what is shown in this graph also, where the duty ratio is varied along on one axis, then the voltage gain is varied on the other axis, and this is for the different number of levels. So for level 1, level 2, level 3, level 4, level 5, we see that the voltage gain increases quite high with the change in the duty ratio. Now here are the expressions for the design aspects of the inductor and the capacitors and then the diodes. Here is a comparison of different proposed converters, and here the types of converters are mentioned as A, B, C, D like this. And here are the number of components that are used, number of inductors, capacitors, and switches, diodes, and total number of devices. Then in the continuous current mode, what is the voltage gain and what is the normalized switch voltage stress, and or if the output is grounded or floating is mentioned here. So this A, B, C, D, they are explained here. This A is traditional boost converter, B is multi-level boost converter, C is voltage lift technique based on non-isolated boost DC-DC converter, and so on. Now the first four, they are called the low voltage gain conventional converter. Then these three, they are called moderate voltage gain derived converters, and this is the proposed one, which is high voltage gain, and it has a grounded output port, so input and output grounds are common. So this is highly suitable for use in the solar PV applications. Here the simulation results are provided for 20 kilowatt, input voltage 36 volt, and only one level is shown here with the output voltage fixed at 400 volt. The load is taken as a resistive load of 8 ohm, and the DP ratio is at 70%, with the inductor values 10 millihenry, capacitor values are 440 microfarads, and the switching frequency is taken as 50 kilohertz. So this is the input voltage that is applied, and so it's not exact step function, but there is some delayed, and the rise time of 0.04 second is given for the input voltage. And then we see the output voltage, and it also rises like that, and it reaches 400 volt. There is a small ripple in the output voltage, and this is the current, output current. There is a small ripple. This ripple depends upon the value of the output capacitor that is connected to the load. And here what we see is the inductor current L1 and L2, they are balanced because we have assumed identical L1 and L2. If there is a mismatch between L1 and L2 values, then certainly there will be some change in this current. And this is the voltage across capacitor C1 and C2. They are quite balanced. And this is the current stress and the voltage stress of the switches. So what we see that it has quite high current stress, but the voltage stress is half of the output voltage. And here are the peak inverse voltage of different diodes. So diode D1 has minus 80 volt, and a diode D2 has minus 35 volt. Diode D3 minus 80 volt, diode D4 minus 200, D5 minus 200, and diode D6 minus 200. This is the experimental result that is tested for a 200 watt power converter with 36 volt input and 400 volt output. So input and output voltages remain the same, but the power is 100 times reduced compared to the simulation values. And what we see that we achieved a good quality of the output voltage and the output current, and this is the input current that has some ripple. So as a conclusion, the paper has presented a new member of modified boost converter with a switch reactive network for 400 volt electric vehicle applications. The proposed converter providing non-inverted output, and it share common ground, so it is suitable for PV integration of electric vehicle charging applications. The voltage gain of the converter not only depends upon D, but it depends upon N also, that is the number of levels. And the voltage stress across the switch is half that of the output voltage. The efficiency of the converter is achieved as 94.5% at rated power. Simulation and experimental results, they validate the functionality of the proposed converter. And these are some of the references that have been used for the paper. And here are the authors of the paper. And the presenter myself is Professor Atif Iqbal. And thank you very much for your listening. And if you have any questions, you can email us on our university emails. And thank you very much for giving us an opportunity to present our paper. Thank you.